All right, so we're diving deep today into a topic I know a lot of you have been asking about, migrating databases without any downtime for your applications. We've got a ton of research on different strategies, and it can get pretty complex. So our mission today is to break it all down, highlight the most insightful parts, and make it understandable for everyone, no matter your technical background.
Yeah, database migration, it doesn't have to mean those dreaded outages anymore. The techniques we're going to talk about really focus on minimizing or even completely eliminating that disruption, but it all starts with really thorough preparation.
So let's unpack that pre-migration phase a little. I'm seeing in all this research that understanding your existing database inside and out is absolutely critical. We're talking data profiling, schema complexity, the volume of data, and really importantly, peak usage times. Why is this deep dive into the current system so crucial before you even think about moving anything?
Well, imagine trying to move a house without knowing how much stuff you have or where everything goes, right? It's chaos. Data profiling helps us anticipate the challenges we might face during the migration. Knowing those transaction rates and peak usage, that tells us what kind of horsepower we need in the new system and how to strategize the actual move. And then, of course, figuring out how much downtime is acceptable, even if it's just seconds. That sets the boundaries for the whole project.
Makes total sense. And then I see this emphasis on classifying the data based on how critical it is. How does that play into shaping the migration?
Prioritizing data by how critical it is, well, that allows us to focus our efforts. We apply the most rigorous and real-time synchronization methods to the data that absolutely cannot be lost or delayed. Less critical stuff, maybe you can tolerate a slightly longer sync period. It's all about optimizing resources and making sure the most important things are handled with the utmost care.
Okay, so planning, absolutely key. Now let's get a bit more technical, starting with schema changes. I keep seeing this expand and contract approach mentioned. What's the gist of that?
What's really fascinating about this approach is that it's super gradual. Instead of just ripping and replacing, we add the new schema elements first, but we keep the old ones around. Then we can update the application in stages to start using those new elements, kind of like slowly turning on a new faucet while the old one is still running. The key insight here is that by making those small reversible changes, we're drastically reducing the risk of a major failure.
That's a great analogy, like upgrading parts of an engine while it's still running. The research also mentions something called database refactoring using temporary tables and views. How do those fit into managing changes?
Ah, yes. Temporary tables, they're like our behind-the-scenes workshop. We can do all sorts of complex data transformations there without the application even knowing. And then views, those act like a stable interface, so even if the underlying schema changes, the application doesn't immediately break. It's all very smooth.
Now, when we're talking about moving to a completely different database platform, dual write seems to be a core technique. Can you walk me through the main idea there?
Dual write, it's exactly what it sounds like. The application is essentially writing to both the old and new databases simultaneously, so you've got this real-time redundancy. The critical takeaway here is that by writing to both systems and constantly validating the data, we're ensuring that nothing gets lost or corrupted during that transition. It's like having a safety net.
And to keep the new database in sync, practically in real time, there's change data capture or CDC, right? I see tools like Debezium mentioned a lot. How does that work in a nutshell?
Imagine the new database constantly listening to the old one, copying any changes almost instantly. That's CDC in action. Tools like Debezium, they're really clever. They can often tap directly into the database's transaction logs. So it's a super efficient way to get that stream of updates.
That's fascinating. And what's interesting is that there are even database-specific tools for this, showing how tailored some of these solutions can be.
Absolutely. Systems like PostgreSQL, they have logical replication built in, and MySQL has tools like Ghost, each optimized for their specific architectures. It really simplifies the process. And then, of course, a lot of cloud services integrate these capabilities right out of the box.
All right, so the data's moving, but how do you actually switch everything over without a hitch? Progressive exposure, using a service mesh or load balancers, that sounds like a really smart approach. Can you explain it?
Think of it like this. You're opening a new store, but you don't just shut down the old one and hope everyone finds you. You slowly start directing more and more traffic to the new location while keeping the old one open. Tools like service meshes and load balancers, they give us that fine-grained control, allowing us to precisely manage the percentage of users hitting the new database. It's a very gradual opening, and we can monitor everything closely before the full switch.
And of course, you need to be constantly verifying that everything is going as planned. Automated verification with checksums and drift detection, that seems absolutely crucial.
You got it. Continuous data validation, using those checksums and record counts, it can really quickly identify any inconsistencies between the systems. And then drift detection. That helps us spot those unexpected changes that might pop up in the new environment. We need to stay vigilant.
Makes sense. And of course, the new system has to be able to handle the load once everything is switched over, which was where performance testing comes in, right?
Exactly. Load testing, it's like putting the new database through a rigorous workout, simulating real-world usage. This helps us identify any bottlenecks and ensures it can handle those peak demands before we make the final cutover. We don't want any surprises.
But even with all this planning and testing, you need a plan B, right? That rollback capability sounds like essential peace of mind.
Oh, absolutely. Having a reliable rollback plan is crucial, no matter how confident we are in the migration. Maintaining bidirectional replication, that allows us to quickly switch back to the original database if we hit any critical issues. And keeping the source database active, that gives us that safety net just in case.
And instead of doing one big risky switch, you can also do an incremental cutover, right?
Yes, exactly. Migrating in smaller chunks, whether it's by specific data areas or services, that significantly reduces the risk. And starting with those read-only workloads first, that can build confidence as we go. It's a much more measured approach.
And finally, I keep seeing database proxies and application-level retries mentioned for achieving near zero downtime. How do those fit into the picture?
Database proxies, they act like intelligent traffic cops for our connections. They can transparently handle failovers, so the application doesn't even know there's a problem. And application-level retries, they ensure that those temporary connection hiccups that might happen during the switch, they don't cause the entire application to crash. It's all about that seamless experience.
So, to sum it all up, it's a layered approach, right? A careful planning, phased implementation with techniques like expand and contract and dual rate, continuous synchronization using CDC, rigorous testing at every step, and of course those robust rollback plans.
You nailed it. All these strategies, they work together to enable smoother transitions, often completely invisible to the end user. That's pretty amazing what's possible now.
It really is. And, when you consider how much we rely on constant data availability these days, it makes you wonder, how far can we push these zero downtime techniques? Could they become completely seamless? And what new challenges might pop up as these systems become even more complex and sophisticated? It's something to ponder. Thanks for taking this deep dive with me today.